talk about the homotopy type of the plane with 0, 1 or 2 points removed. And so if we don't remove any points at all, we've just got a plane like this, then and this is easily seen to be contractible. We can just do a linear homotopy, a straight line homotopy given by this formula here, that ht comma xy is just tx ty, and that just moves everything in a straight line down towards the origin. And so if we take t equals 1 at time 1, so this picture here represents time 1. h1 comma xy is just equal to xy, and so h1 is just the identity, and then this end of the scale represents t approaching 0. As t goes to 0, you get h0 xy is just the origin 0 comma 0. But here's the picture when we remove a single point. Okay, so we're going to remove this single point of the origin from the plane and see what's the homotopy type of what's left. So we've drawn a red circle around the removed point, and because we've removed that point, we can stretch everything else back onto the circle. You see, so points just to the right-hand side of the circle moving out to the right, points just out to the left of the circle moving out to the left. So that would create a discontinuity if if we'd sort of left the origin in as part of the domain of this function we're trying to describe. But because we've removed that point, this issue about different points moving in different directions is not relevant. If we want to see that in terms of an actual formula, I mean, we can write a formula as we've got here. So we define this function ht comma xy is so we take this vector xy again here and we multiply it by the scalar in the brackets. The scalar is 1 minus t plus t over root x squared plus y squared. So t equals 0 because this term goes away, and then the 1 minus t term is just equal to 1. So t equals 0, we've just got h1, so h0 comma xy is equal to xy. So h0 is the identity. On the other hand, t equals 1, this 1 minus t is just 0, and so what we've just got is xy divided by root x squared plus y squared. So that's the usual sort of normalization. That's the unit vector pointing in the same direction as xy, so that will lie on the red circle. So what we're doing is we're just kind of moving. Each point moves on a straight line to the closest point on the red circle, and that's the effect of our homotopy. And you see, and here we've had to divide by root x squared plus y squared. Of course, that would be a problem if the origin at 0, 0 was part of our domain of definition, then we'd be dividing by 0. But the whole point is we've removed the origin, so root x squared plus y squared is never going to be 0 in our in the domain that we're talking about, and so this is a well-defined continuous function. Now let's have a look at this picture here where we've removed 2 points. Now we've drawn 2 circles around these points which meet at the origin here. So we take this space, then again we can retract it onto the union of these 2 circles. So the points inside the circles are just kind of moving outwards to the closest point on the red line. The pattern of what's happening outside the circles is a little bit more difficult to describe, but basically everything is just kind of moving inwards towards the pair of red circles, this kind of figure 8 shape. And and so the conclusion of this picture is that this space R2 with 2 points removed is homotopy equivalent to this union of 2 circles, which we call E. We also use this notation S1 wedge S1 for the union of two circles meeting at a single point, and that's homotopy equivalent to R2 with 2 points removed. If we wanted a more formal proof, we'd need to actually write some formulae, but that can be, which is not so hard to do.